Okay, for this section, we're going to see if we hopefully have sense enough to do these in JASP. So, as soon as I get this out of the way, we're going to be using mainly this statistical analysis JASP book for these because it gives a great step-by-step guide and it gives a fantastic way to write up the results at the bottom. And we will start doing that soon. Um, I think you'll have 4 total little case studies where you'll have to figure out which test to use. Um, Solve the problem and write up the results, and they're not that hard. So starting here, and the other textbook kind of goes off. There's a lot of good information, but it kind of leads you way down some windy paths. So read them for the information on hypothesis testing, but yeah, don't get too caught up in them. So we're going to be starting. We can start at page 43. We'll look at what an effect size is and how to calculate it. One sample t-test. We'll skip the binomial and multinomial. So we're going to go through we'll go through all the assumptions for the one sample t, 2 independent samples, and paired samples. The main assumption for any t-test, continuous dependent variable, and for one sample comparing seeing if the mean of that population based on the sample differs from a set benchmark or hypothesized mean. So we got a certain standard or historical value. We want to see if it's different. We may want to see if it's less than or greater than. For right now, we're just testing the difference. So that's got to be a dependent variable, normally distributed, usually randomly selected, and independent, making sure there's no other outside interference, acting on it. So I'll show you how to test these assumptions for normality. For the 2 sample, there's 2 different ones. For the independent t-test, we have studentized, which the assumption there, in addition to all these, that we have independent samples not related to each other, normally distributed with large enough sample size to matter, um, normally distributed. We also are assuming that the variances are similar or equal, similar enough to be assumed to be equal for both populations. So remember, for a t-test, we don't know the population parameters, and usually in business we won't. So even if we do know, a lot of times we'll still use a t-test, simply because that's what all these are set up to do. So if we determine that the variances are different, that's when we won't use a studentized t. We'll use a Welch correction, which is a different kind of t. Basically the same thing. It just makes an adjustment for larger variances, that may cause, more differences. Then we will learn for a paired sample, we're just looking at 2 within samples. So it's going to be like a before and after, where each respondent tests before and after the manipulation of the change or whatever, or rather than having, whereas an independent sample, we may have a control group versus a manipulation or an action, as long as they're both randomly assigned to the groups, or we may just be comparing 2 different groups of the same variable to see if there's a difference. For a paired sample, we've got responded at time 1, responded at time 2, and we're seeing the difference. And rather than comparing, for the paired sample, rather than comparing the means of each group to determine if the difference is significant, uh, we're taking the means of each line and then taking the mean of the differences to compare. So by doing that, we're controlling for any outside factors by using the same respondent at time one and time two. So it's an internal sample, So I'll show y'all how that works when we get there. And if that one's not normal, then we'll use a Wilcox assigned rank. If the two independent samples are not normal, we can use a Mann-Whitney U. So and basically those use medians instead of means. So we can go ahead and start by looking at our effect size. And these are different effect sizes and ways that we interpret them. So for everything we're doing this week, cohen's D is going to be what we need for parametric. And we'll be using rank by serial for somebody's typing in while I'm trying to record this. So I'll just wait. So rank by serial for non-parametric, but mainly what I want y'all to know is the parametric. So because we're going to be dealing with normal distribution most semesters. So anything less than 0.2, it says trivial, is probably, even if it shows significance, the amount of the difference, even though the difference may always be there, and that's what significance basically tells you, the amount of the significance may not be large enough to make a difference. So it's going to be too small to matter. A small size, 0.2 and greater, is going to be small but meaningful for business decisions. Medium, 0.5 to 0.8, and then anything over 0.8 is very large. And, so the larger this effect size, the lower sample size you can have and still have power. Your power to a given, sample size determines your ability, to detect an effect size at these levels. So it's all interrelated. For your beta. Remember, your alpha just determines the probability that you're willing to accept that the actual difference won't be there. And, the p-value is the probability of it not being there. So it doesn't necessarily give you a size or an impact, whereas an effect size gives you better than that. And your power tells you your probability of getting that result at the alpha level. So those are kind of the different terms we use and how we use them. So let's go ahead and load this one sample and try to knock it out really quickly. So the file we're going to be using here, one sample t-test. I have those loaded in somewhere within the week 4 introduction. I know it's a long one this week, but it's a lot to learn. It's going to start being longer and longer. So if you look here, example data from statistical analysis and JASP, one sample, independent, and paired sample. Those are the ones we're going to do, and those are the ones we're going to use. That's where you can get them. So download them, save them to the computer, and then we'll come to JASP and load them. So open computer, wherever you got them stored. I got mine stored in this file, so I'm going to scroll down. I've got them all because I went to GitHub and downloaded the whole thing. So here we got, I've got that loaded twice, do I not? We need one of them. So let's close one. All right, so he doesn't show, but I always do, is just go ahead and run descriptives and make sure I don't have any missing or anything looking terribly out of shape, because we scroll down, so we don't want to see any single digit numbers for height for, looking at centimeters, because these numbers are height in centimeters and mass in kilograms of adult males in the UK. And that's why we're using centimeters and mass in kilograms instead of feet, inches, and pounds like we would in good old US. So, and we're determining if these are different than the stated amount, 178 centimeters and 83.4 kilograms. So, now that we've looked and seen, we can go back and kind of got our descriptors here. We don't really need anything. We're just kind of seeing, making sure everything looks, plausible. We got some pretty low weights there, but we are testing if they've changed, so that's okay. If you wanted to plot all the differences, I mean, it's fine, but right now we're just mainly looking, nothing's missing what we got for our initial sample, so we can close this. Now we'll go to t-test and open one sample t-test. So we're going to test height first because that's what the book does. And you can tell right away we've got a very high T and very significant P. That's because we have not put, and I'm going to go ahead and name this one height. We haven't put our test value. We're testing against what, 178? Yeah, 178 exactly. That's where we put the value we're testing against. So now you can see that's dropped down because we're actually testing the actual difference. So first thing we got to do is test for normality, make sure we're good to go here, and we are, because this Shapiro Wilk, that's a test that you want to fail, and it even says right here, significant result suggests a deviation from normality. So right now we can tell that that's very normal. Excluding cases per variable and listwise. This is what I didn't get to last week because it's only within certain tests. So per variable, that's what we call pairwise deletion, which means we're only deleting part of the pair that matters. So if we had one of these missing and not the other, we would keep the line so we could use it for height, but not for mass if that's one missing. Since we're only really testing the mean of one and its standard deviation, using those to determine a confidence interval to test against this 178. So we're taking the mean here, subtracting 178 from it, and seeing if it's different from zero. That's our actual null hypothesis there. Or actually, we're testing whether it's different from 178. But the way we do that to get our actual critical value, and we subtract one from the other and see if it's different from zero, because that's how we do our two samples. If we were testing if it's increased or decreased, we could use a right tail for increased, a left tail for decreased right here. But right now we're just testing if it's different, so we're using a two tail. Listwise deletion, if either one of these were missing, we would delete the whole line, which is what y'all have normally been using, either listwise. I showed y'all how to do mean replacement where you did a log transformation. We can't do imputation because it's not in JASP yet, or Jamovi, whichever one you're using. They're both the same with the exception of Bayesian, which we're not going to get to anyway. So, the location, this tells us our actual mean difference here. Click on the confidence interval. It tells the confidence interval for the distance. I always click that even though the book does not tell you to. Because if you wanted to know if it's at least a certain amount, if you wanted to know if it's at least 5 different, that's the only way you can do it, because this doesn't give you, unless you added 5, but then that's only going to be on one side and not the other. So this is really the only way you do it. Just tell if the upper bound or lower bound is at least. Here we don't have any difference based on our numbers here. So our effect size, based on our effect size, we don't have any effect whatsoever either. So even though these are different from these T, they're kind of going to work because if you got a stronger effect, you're going to have a stronger T, unless you just have a monster sample size. Then you can have a small effect with a larger T. You can click the confidence interval, but we normally don't. We just normally use what it is. Because if it's going to be low enough that a confidence interval matters, then it's probably going to be too low. If you had a effect size of like zero point 0.2 or like 0.24, you might want to run that to make sure it's always. But if it's above it, we're going to go ahead and assume that it's small but meaningful. Here's our descriptives, so you can get the mean value, the standard deviation, standard error, and coefficient of variation for our sample. 23 sample size, so n minus 1 for degrees of freedom 22. That's where that comes from. Your T, like I said, is going to be your your difference over your standard error. And he said to go ahead and click your plots. I always click horizontal display on my rain clouds because I think it makes it easier to see. But as you can see here, the hypothesized mean is within this box for our confidence interval for the mean. If we wanted to actually see what that was, since it only gives us the confidence interval for the distance, we could go into statistics here and just calculate it, and that'll, that way you can see for height 175 to 179. So that's what this chart here, 175 to 179, that's our 95% confidence interval for the mean right here. So our actual hypothesized means dead in the middle, so it's not any different. This value would have to be out here or out here to be in the rejection range. This is the whole sample, but this is the confidence interval for the mean, and that's what we're testing. So that's how you do that one. So now he says go ahead and try the other one. So t-test, he said the book says just drop the mean and keep all the check marks, but I like to do them both. So we'll call this one mass. We'll load it, and first thing we have to do is we had 68 point what, or actually 83.4 is what we're testing against. 83.4. Why did that not work? 83.4 is our test value there. To use a student's T. Now you can do a z-test if you have the population, but normally we just using students. So, and we're just testing different for this one. We got to test for normality. Use a z if you know the population standard deviation. And you would have to enter it. Right now we don't. So we're using a T. BM excluding pairwise. Got our test value in. Normality. Although it's closer, we are still not significant. So it's normal. So we come over here, look at our location estimate. Again, I do always click those just so I can tell. You may want to know if you're at least 15 different, or if you're at least 10 different, yeah, you're good. Well, actually, no. You would actually be at least 7.4 difference. So our effect size, look, we got a very large effect size because you always look at the absolute value of this when you're looking at those, and anything above zero point 0.8. So we got an extremely large effect size due to the large actual difference, even though our sample size is fairly small. Um, Descriptives gives us, descriptive statistics here. If you only wanted to, look at those here and not use the actual descriptive plots or the actual descriptives in the. So here we're looking at our plots. Here you can see our hypothesized difference. Here's our confidence interval for the mean. So yes, it is significantly different. It's still on our rain cloud plots. Again, you can leave them that way. I like to turn mine sideways. So if it's outside this confidence interval, it is significantly different. Here we're in the rejection range, so we reject the null. You're 95% confident that you reject the null and accept the mean. So here's how you get that. So if you want to know how to get the actual power of these, you can go over here and click power, and it'll tell you. You can go ahead and enter if you want to determine the sample size required for, what was that, effect size 1.4. For a minimum, we usually want 80 power with an 0.5. So for a two-sided, we want no one sample t. So for a two-sided, our required sample size for that large would be 7 to detect, which is almost unreal. But if we were only looking for a medium effect size, we'd need 34, which we don't have. So let's look and see what power we have based on our. And you do this with any. I usually use it for a program called G Power. It gives me a lot more to choose from than this, so it is still useful to me. But for simple tests and stuff like that, it's nice that they put this in here in recent years. So we got 1.4. We're looking for 80 power, but we want to see exactly what the power is for one sample. Our sample size was what, 22, I believe, 23. So our actual power based on this, and it'll give you charts there and kind of see as it grows out. Power curve by n is actually useful. So we want to be in 80 power range. So based on this, we've got all the power we need because that effect is large. If we wanted just to pick up 0.8, we'd need 23. We'd have 95, 96% power. If we were just looking to pick up a medium based on this, look, we don't have 80 power. So, and that's how you do it. So, and you can also determine your exact effect size based on the desired power and that. Mm, so our effect size for a medium at 80 power, 61. So that's kind of how we do that if you wanted that. And now the only other thing on this one is what's useful here. We determine, now we need to know how to write these things up. So start and he'll tell you exactly what I just told you about how all those for both tests and here reporting results. Make sure you look at reporting results here. So for both of these, we're going to report the results of both. For one sample, they're very easy. You just tell whether or not there was a difference or whether or not one was significantly larger or smaller if you're using the left or right tail, or right or left rather. And then in parentheses, put your T for 22 degrees of freedom equals at your actual T, and that's your P. Then he puts, however, distance was significantly lighter than UK male population average, but we weren't doing a one sample over there. We were doing, I guess it didn't matter, but that wasn't what we were told to do, was it? 7.159. If we were doing, if we were testing, if they were, I mean, the T is not going to, it's still going to be the same because that's your actual test value. Is not going to change. Your P value would change though. Well, actually, your T value would change because it's the P is the probability of the test statistic, which is the difference over the standard error. But the probability is going to be twice as strong for one tail. So, I mean, I guess you could report it, but normally you just put different. They were significantly different if he told you to, but that's how you report it either way. Negative. I guess he's just determining based on the negative difference that it is lighter. Um, but normally, if you were testing to see if they were lighter, you would choose a left tail test. So that is one sample. We will come back in just a moment to do two samples. All right, so for this one, we are going to work on the two sample t-test, which is listed as comparing two related groups in the book. Or no, two independent groups. These are independent t-tests. So click on that one. It's going to take us there. You can see that's the T. Rather than comparing, saying the mean minus the hypothesized mean, we're saying the mean of group one, and that is mu, minus the mean of mu two over the standard error of the differences. And we have to calculate the standard error a little bit differently for these. We got the standard deviation for, if we can assume that the variances are equal on these, we got, basically the variance 1 over its sample size plus variance of 2 over its sample size. Sample sizes need to be similar but don't have to be equal. Basically, one shouldn't be more than 50% larger than the other. That's kind of the rule. So, other assumptions here, group independence. So each one has to either be randomly assigned to a group if you're using a control group and a control and some sort of manipulation or effect. So a treatment, or sometimes you may have two nominal groups. When you want to compare the same variable of them, maybe you want to see if customer um, customer preference for a certain item is different in Boston or Atlanta. Well, obviously, you're not going to randomly assign people to Atlanta or Boston. You're going to use where they're at. because that's part of what they're from. But you should randomly sample from each city. So that's how you determine that. What you don't want is one thing to be causing another, or in the case of the paired tea that we'll get to next, we have it's in the frost advisory. That's great. We have a situation where we got a time, a respondent that does time one, and then the same respondent at time two. So if you got two items within each sample. So, and you'll understand more on that when we get to it. So right now, we've got independent groups from normally distributed continuous dependent variables. Can't have any anomalies here. Here's the difference one: homogeneity of variance. So the variances have to be similar. And remember first week when we were looking at the heterogeneity and homogeneity, and we're saying we don't want the variance of one to be, all on one end and skewed, and the other one, to be fairly. We want the variance to look fairly equal across both samples and similar. So you can see unequal variance and equal variance here. This is fairly similar. This, you got not much variance here, and spread out on this one. So I'll show you how to test that in a minute. Well, actually, we're there. So we have to have continuous dependent variable, normally distributed. Both groups need to be independent of each other. In other words, we're basically testing the two samples are testing two populations, even if they're two populations for the same variable. It's two different groups. Two, they're not um, monolithic. I mean, it's so here's everything how to do. We're gonna he's clicking both so you can do it, but we're just gonna go ahead and do it. Test one and then test the other. So we'll go ahead and load the again. I sorry about all the scrolling. I know it makes y'all sick, but independent t-test from where I showed you now the other day. So I'm gonna go ahead and open where I know I have mine and independent t. So there we go, and it's loading. Here we go. My height and mass is still up. I can close that one up. Okay, so I thought it could. There we go. Don't save. Okay, there we go. This little thing gets on my nerves. I just had it out with Copilot. It couldn't help me find my file. So here we got males and females. Okay, obviously you weren't randomly assigned to one of those groups. You were born with it, depending on who you ask. Um, and the amount of weight loss in a weight loss program. So we're going to see if one differs significantly from the other. So, like I said, no matter what the book says, I always run descriptives just to see. So put our variable in here, and then we'll split it by nominals. So now I see we got no missing. Samples are fairly similar. The means look, yeah, they look fairly different, but the standard deviations look similar. So it looks like the variance is the same, even though the means are different. And that's what we're trying to test. Do women lose more weight than men in this program? Apparently they do. That's enough for now. We can go back, and now we're going to go to t-tests, and we're going to pick independent samples this time. So we know we got our scale variable. Can't be anything but scale. If you try to load ordinal, it messes you up. Gender, actually you can do it, but you just had to choose a different test. So he chose both of these to show the difference. Not a lot of difference, but if this isn't normal, then you have to pick the Welch test instead of student. If excuse me, if the variances aren't the same, you have to choose the Welch instead of the student. If your data aren't normal, then you have to choose Mann-Whitney U. So right now we're going to test for normality by clicking normality, and it pulls up, lo and behold, superior wilt. So p-value is way above the significance level, which means we are normal because this test checked for non-normality. So now we have to check for equality of variances. It's going to default to Brown Forsyth for whatever reason, but we always use Levine's. That's kind of the gold standard when we're doing this. And we'll use that next week for ANOVA too. So Levine's test, you can see it's more stringent because Brown's, well, not much more, but it is, the p-value is a little bit smaller. We got degrees of freedom here. Uh, yeah, both of those -2. Yeah. So that's where we're testing our quality of variances. Since its p-value is above uh, level of significance, we can say that we have similar variances. We have homogeneity variances are similar throughout. So again, there's exclude cases. Go ahead and click pairwise, but we don't have any missing variables, so that's kind of just doesn't matter which one you pick. Okay, so we leave it on student T because we are normal and similar variances. So that way we're using a pooled variance rather than the Welch test, which, splits variance. So a pooled variance, we're basically just looking here and grabbing the proportion for each one, like I showed you. Um, so click our location parameter, and I always click the confidence because I like to know how much. Looks like, and that's for the difference now, not for that's for one minus the other. So it's not, for like we had. Well, actually, we did have one minus the benchmark last time. Okay, so p-value, our degrees of freedom, both of these -2. So that's 87 -2. Or actually, the formula is n1 -1 plus n, but it's the total sample size -2. There's our t-test. That's, again, highly significant. It's very large. So now we need an effect size. Cohen's D. That's our test for normal samples. Again, very large effect size, 1.3, because that mean difference is fairly large for, you got an average of 3.7 and a difference of 3.2 over here. So that's, the difference, it's nearly twice as much. So then, it's obviously going to be significant. So, and then we can click our plots and rain clouds and descriptives, just like they did in the book. And look, that's obviously the confidence intervals don't come close to each other. So you might have a little overlap here, it looks like on this, but I don't see it here. So certainly not enough to be significant. So looks like we've got females that was, yeah. Um, so we got that one. So we'll get to how to write that up in a minute. So next, what else were we going to do with this one? Test normality. Why did it? Group 1 is not equal. Our test of normality only gave us 1, didn't it? For weight loss. It didn't split it. Was it supposed to split it? It's probably just an update with the different versions. Of course, he had those. Oh, no, still didn't change. The group descriptives are different. So, uh, Still not the same either way, because I don't know where you got this. Excuse me. So quality variance, that's exactly the same. Our mean difference, that's just one minus the other. It's going to be the same no matter which test you use. The only difference is how the test statistic is calculated and degrees of freedom for the Welch. It's on that sheet with all the formulas I gave. If you want to see the lights, it's huge, or the Excel sheet with all the program, all the summary statistics already programmed in. You can find it there too. Um, Here's our plot. So these don't look significantly different, in the rain cloud. They certainly are when you see that's our confidence interval and that's our confidence interval. So, and then how do we report the results? The Levine test found that the assumption of homogeneity variance was met. And then you show it uses an F test. That's how you test the difference in variances. So F1 equals 2.28P equals 1.35, and that one sample. Um, Shapiro-Wilk test shows that both groups have normally distributed data. So you're showing, well, actually, ours is only going to shows that the sample has normally distributed data, and then you'll put W equals whatever we got here, 0.991, 0.895. So that's how we would do it because we were only given one. Therefore, an independent sample student t-test based on equal variances was carried out. Okay. Showed females lost significantly more weight, even though we didn't test, which would have affected our piece size, but not enough that it would have shown up uh, over 10 weeks of diet. And then did males, who had a mean of 3.72, standard deviation 2.56. That's just the mean standard deviations, and then colon and put the test statistics. T of 85, that's degrees of freedom, equals 6.16. Go ahead and, 6.1. Go ahead and write the zero there, 6.160. P value of less than 0.001. And again, don't put P equals zero. Don't put, it's got to be less than 0.001 because it's not equal to zero. Then you put the effect size. Cohen's D suggests that this is a large effect. And that's how you'd write that up, and that's how you will. Here's a Mann-Whitney U. So if you got, and that's going to be a different, well, if you had non-normal data, which one was Mann-Whitney? This testing like pain and I can't remember. Hurry up. See how quickly we can do this. So we've got control and ice. So for pain score or treatment is nothing and put ice on it. Sounds like a true Gen Xer right there. So go ahead, look at your pain scores. I mean, actually, it tells us to make sure. So let's go back in here, and I think it says to set the pain score to ordinal. So we show that we don't have a. Not only are the numbers not normal, they're not supposed to be. We can't assume um, interval value. We can only assume order. So our descriptives here, that in there, and treatment, and you'll kind of see we got 15 for each. Should be randomly distributed. Chosen, we've got mean values that are very different, standard deviations that are roughly different. So min and max are very different too. So we'll see. So now we go to t-test and independent samples. Now notice it's got this, so when you move this over, it's going to give us a little thing telling us to, something a little different here. It's still going to do it. So when we test normality, we know we don't. So pretty close to being significant, but you don't even have to test if you're using, because it has no assumptions of normality or variance. You don't really have to test either one of those for the book. So you just enter Mann-Whitney, and it gives us a U. So you can hit location parameters, effect size. You can even put confidence in it. But so look here, what our effect size? It's using the rank by serial. Remember that those were different. I think what was the let's see here, find my table of content. I wish this thing had a back to the front button, but it doesn't. Man, no, that's not what I wanted. I wanted effect size. Effect size right here, 43. It'll scale down to 62. So for non-parametric, yeah, less than 0.1 is too small. 0.1 is small but meaningful. 0.3 is medium. 0.5 is large. So interpret them differently. And what do we have? I don't remember. That's okay. We got 0.8, so that's large. But for some reason, in his he gets off track here and it's kind of mixing, matching what he has. Showing a 0.84 here. Did we have a 0.84? Yeah, we did. Large effect. Okay, well that's easy. Somewhere in here he wrote he halved it for some reason. I don't know why. Maybe it was on the other one. So we got the Mann-Whitney um, effect size. It's going to change that to biserial, not so you can plot it and rain cloud it. I guess if you want to, but it's not. Yeah, actually you can't, or you can do the rain clouds, but the plots aren't going to show up correctly, and neither are the descriptives, because here's why. It shows the mean and standard deviation. This is a non-parametric test, so we have to use median and mean absolute deviation. So we go back to our descriptives and unclick mean, click median. Unclick standard deviation, click MAD. We don't necessarily need mean and max. Then you can come down here and customize your box plots here and label your outliers and make them all pretty. So now you show them we got a couple of outliers here, which they're non-normal, so we can't assume that you're not supposed to be there. And we have our median MAD. I think we normally click interquartile range there too. And yeah, now we got those to report. So when we write it up, show that ice therapy significantly reduces pain. Median equals 3 compared to median equals 7. And those are ordinal values, so they're discrete. And then you put the W or U, yeah, W, 207p less than 001, and then the RB for the rank by serial. Suggests that this is a large effect. So that's how you write it up, and that's how you do it if you have non-normal data. So this one's over, and we will come back in a minute and learn how to do paired T's. Okay, so now we are coming back for the final step for this week, and we are learning to do paired T test and JASP. So paired T, unlike an independent sample, means the sample comes within the group. So as you'll see in a minute, so here the thing we're looking at a pre-diet body mass versus a post-diet, body mass, and seeing if they, the groups lost different amounts of weight. So be comparing one to the other to see if there's a significant difference based on this treatment or diet group. So, and for a paired T, rather than, like I said, the independent samples, you're comparing one mean versus the other to see if the groups are significantly different, or population significantly different. Here, you're comparing. So you're comparing the difference of means with independent. Here, you're comparing the means of the differences. So you're taking a difference for every sample. Then, or actually, let's see if I can find what I got here. Yep, that's not it. I'll show you. Here we go. So the file we're going to be looking at is parity, and that's that. If I can get it to open, I'll show you in Excel really quick what we're doing here. So if we wanted to do this in Excel, and we got the samples here, we could easily go to the data analysis tool pack here and scroll down, select paired two samples, and then look at sample one, and then, down to 79, sample two down to 79, click labels because we got labels there, hypothesize mean. So that's where you're allowed to do that in Excel, but not JASP. So I wish they would add some of those features, but it's okay. We're going to open a new worksheet. So that's going to give us our answers really quickly. So here we got the mean for first group, mean for the second group, the variances, observation for each. They have to be the same. You can't have any missings because it's comparing one to the other, kind of like a correlation. Like I said, it limits any outside interference. So it controls for everything because you got the same people at time one and time two. There's your T-stat, which is what we should get in a minute. And our two tail significance and one tail. So depending on whether you got forward or backwards, it's going to be, whether it's positive or negative. Your critical T, which again, JASP doesn't give us critical values. That's where we have to get to the difference, or the average, the difference of the averages, or the averages of the differences have to get to be significant. So what does that mean? Let's go back. So if we were actually doing this, we would have a difference column, or a D. So how you get this is equal this minus this and roll down. So now we're going to take, now we're going to take, equals average of all these and equals standard deviation sample for all these, and our sample size 79 because these are the same. These are same respondents. So that first week, the one with the birds or whatever, with night owls. That's the one. It actually had a paired sample, and some of y'all caught on to the fact that it was one respondent, so you put half the the response size. I wasn't expecting you to do that, so I was counting each row. So good job. So here's our standard deviation variant. So if you're using this spreadsheet that I put up here, and you're welcome to, you just have to enable macros. And if you can't get them to enable, then you go into the folder, you got it, and right click and click on properties, and then go, it'll say enable somewhere on there. So you can enter that's the, see, that's D bar. So that's the average distance. That's our test, 0, number, sample size 78, standard deviation 2.56, and whatever you want for your alpha. And again, there's our T value, which is pretty much the same as what we got over here, 13.05. Yeah, we got 13.04 there. Now we got 13.05, probably because I rounded off the variance. And P value far less than 0.001. And again, if we want greater than, we're going to be way over here. If we want less than, we're going to have pretty much the same results there. So that's how you use the paired T in here. And if you had independent samples and you wanted to actually use this, if you only had summary scores and not the actual data, the Z-test is up top, 2-tail, 1-tail, and it'll tell you your critical values and your degrees of freedom. It won't tell you your effect size. You're going to have to calculate those on your own. So Welch test is in orange, student T's in blue. One sample, so all of these are there. If you downloaded it, welcome to use it. Just have to enable macros to make it work. So now I have to close this out so we can load it in JASP and show you how to do it in JASP. So the assumptions: dependent variable is a continuous scale variable. Normally distributed, approximately normally distributed, no significant outliers, and the independents are going to be two matched categories of the same variable. So, usually you got a time 1 or time 2. Sometimes, sometimes you may have different months for just, for store, I don't know, different months for regions or something. You want to see the same region, perform differently for seasonality, or seasonality differs, across all of them. So let's go ahead and load that same matched paired t-test. So here we go, open a computer, and right here, and we'll click on paired T this time. So as it opens, okay, and you'll see here, so we've got pre and post, and you can go ahead, like I said, and click descriptives if you want, just to make sure you got no missing, nothing. We're expecting this to, left to be, the right to be a little bit lower because it is diet, but the standard deviation's higher. So is that really significant? That's what we want to know. The min and max seem to be the same for both. So somebody didn't do, unless those are different people. So let's go to t-test here and click paired sample. So now when you click this over and you go pre, it's going to set this up. SPSS does it the same way, and then you match post. So here you got our degrees of freedom, 77, because we had a sample size of 78, and this is all one sample, so that minus 1. So we need to check our normality. We're good. Now our location, that's going to be the difference between each item, or the mean, not the mean, the difference of the mean, or the mean of the differences here. Standard error of the difference So this over this is obviously going to be fairly large. And we've got a T of 13, so it's going to have a significant difference here. Put a confidence interval here. So we're confident we got between 3.4 and 4.3 pounds lost. Is that significant? Obviously it is. So what's the effect size on that? 1.4, very large. So, you can type your descriptives and your plots and your rain clouds, all of this. And what's it going to show here? There's your difference. You can see all of these are pretty much all of these are look like they're headed down maybe. This doesn't look like it's significantly different, but when you match those pairs, it only takes, you don't have to have both samples completely different. You got to have a little bit of difference with every line. So you do this, we didn't have any outliers. I mean, you'd want to include those list wise for this one, or it won't run if you had any. So let's see what all he put here. Everything I had except for he didn't have the rain cloud plots here because they're kind of messy, but actually I kind of like having them there because it shows you every line is just a little bit, and that's plenty enough to make it highly significant. When we were testing against 0, and we ended up getting from 3 to 4. And again, when we're talking about significance here, if you got a large sample size, even the tiniest of differences could be significant. You could have 0.1 at the bottom of that confidence interval. It's going to be significant as long as 0 is not in the middle of it. But you'd have a significant value for an effect that doesn't matter. I mean, who cares if you lost 0.1 pounds in 10 weeks? So that's where you get p hacking, like your discussions are talking about. You find ways to get significance of 0.05 just because that's kind of the academic standard, but it's just an arbitrary number made up. And I mean, we don't. I mean, what does P05 mean? 1 in 20 chance that you could be wrong, but even if you're right at 0.1, if that's your lowest, confidence level, is that a significant difference? It's statistically significant, but it's not useful for decision making. It's not practical. So that's why you kind of need, and p-value doesn't tell you the strength. The effect size tells you the strength, and so that's kind of, it's tied in with your power. So I showed you how to do all of those, how to fetch all of those numbers earlier. If you want to determine power or play with your effect sizes. So now how do we write these up? Pure root was not significant, suggesting that the pairwise difference were normally distributed. Therefore, the assumption is not violated. And then you put your pure root, score here and p-value. Then post diet body mass was lower than at the start of the diet. So you got the mean standard deviations for both of those. The mean difference shown to be significant. So you get those from your mean standard error here. From your t-test score, and then you write the value of the test to show how significant, and that's going to be t of 77. What I just did. Okay, t of 77 equals, and that's your degrees of freedom, remember, unless you get real fancy and actually use a sub, but this is fine. T of 77 equals 13.4. That's our t-test, comma, or insert our test statistic, comma, and the p-value. And then one last statement, Cohen's D of 148 suggests that this is a large effect, actually extremely large effect. So if they weren't significant, we'd use a Wilcox rank. And this is the one, on the last one I told you, he kind of used different. So he used pre-anxiety and post-anxiety, but he's still got, the paired samples for this in there. And then he halves the bilateral rank for some reason. That's 0.92, but he put half of what we had up here. So I don't know. It's kind of got messed up. So for non-parametric distribution paired test, you'd use Wilcox and sign rake. If you really want to know how to do those, go look up my dissertation somewhere. I did a bunch of them. So other than that, let's just stick with the T and call it a day. So these are the three types of tests you're responsible for, all the assumptions, how to figure them out, how to determine which one to use for each one. So that should get it for this week in JASP. So thanks for stopping by, and I hope this helps.